Good morning, everyone. Thank you for joining this webinar. So we are going to have an online course on IoT and AI for the Waziup. So today we are with Congduc Pham from the University of Po, and he's also with Javier Mantila, also from the University of Po. So thank you. I think we have a good number now. We can start. Over to you, Congduc. I think you're on mute.
Sorry, yes, I was muted. Sorry. Okay, thank you, Wilma, and good morning or good afternoon, everybody. It's a pleasure to have all of you here. So, as Wilma said, this talk, this webinar will be divided in two parts. I will take care of the first part, presenting the basic concept of integrating IoT and AI technologies. So this part really focuses on AI, so artificial intelligence, for adding these features to IoT infrastructures. I believe that all of you had the introduction to IoT, where we presented the IoT ecosystem and all that stuff. So really this part is going to focus on the AI part. And after my presentation, that would probably last for about 45 minutes, then Javier Mantila will present in more detail how these AI features are going to be integrated into the Waziup gateways, and how we can build something that is easy to use and still provide advanced AI features for IoT applications. So I have two slides, preliminary slides, describing a little bit what we have been doing. So Waziup has proposed two technology parts, one for the sensing parts, where you can build your IoT devices, and the other one for the control part. The control part is mainly the gateway part that receive data from the sensor part. And the purpose of doing all this is to really propose something where you can adapt to various application domains, and then collect data, and at the top of the high-level layer here, you would perform data analysis, optimization, and control. So this is the part where we're going to be to focus on here, because once you got the data, maybe one of your most important or probably most difficult task also is to how to analyze it, how to find correlation, how to optimize, and maybe apply control. So here we're more going to talk about the data analysis part, maybe a little bit the optimization part, but not the control part, because the control part is probably the actuation part, and that can be probably explained a little bit later on. So the whole idea is you start from what we have right now, which is the Waziup. The Waziup gateways embeds a lot of possibilities to run locally applications. So the purpose of adding AI is to be able to add a whole AI frameworks, and that is the pictures in the right part of the figures here. But of course, Javier will describe this in much more detail, but I just want you to anticipate a little bit, just to put the big pictures so that you see what I'm talking about. So taking this as an example, if you manage to add the IoT gateways, the traditional IoT gateway, adding the AI parts, then the purpose is to try to build a fully autonomous system. What I mean by fully autonomous systems is the system that collect data, IoT data, will be able to use historical data in order to perform some prediction on the behavior of the physical system that you are monitoring, okay? And depending on the applications, but most of the applications usually requires integration of multiple knowledge streams. So if I take let's say the agriculture irrigation problem, which is one of the most well-known smart agriculture applications, then in order to optimize usage of water, then maybe you would have to integrate data or parameters that could be the irrigation techniques, sprinklers or furrows or flooding, whatever. The soil type could be semi-arid, arid, dry, whatever. The geographical areas, the crop type, maybe it's maize crop, maybe it's wheat, and it's completely different from one plant to another, and probably also weather data, okay? So integrating all these multiple knowledge streams allows you to, at one point, when you manage to integrate the right AI technologies, at the end, you may end up with a fully autonomous system, and what I would call the whatever in the box solution. Okay, so in case you're interested in irrigation, it could be smart irrigation in the box solution. If you're interested in something else, it could be something in the box solution. But the idea of in the box solutions means that the whole system could be autonomous, providing useful feedbacks to the user by itself. Okay, so this is to set up a little bit the context of this talk. So what we are going to talk about is what could be referred to as IoT back office. Okay, and when we're dealing with IoT data, usually it means big data. Okay, it's not explicitly said, but sometime or most of the time, you're going to receive a lot of raw data. And there's these nice pictures from IBM that say that when you're dealing with big data, you have four actually issues. First, the volume of data, of course, okay? But then you have the velocity of data, because data can arrive very quickly. It doesn't mean that data from one sensor arrive quickly, because maybe one sensor is going to sense one data every, let's say, 1 hour, for instance. But if you have dozens or hundreds of sensors sending data every 1 hour, then data could arrive quite fast. You have also variety of data, which can come in different format, or it could be complex data, it could be simple data. Some of the data may have correlations and so on, okay? And one of the main issues that I'm not going to address this specific problem here, but just to make you aware of this problem, is the veracity of data. Because some sensors or some nodes may have problem, may be probably not enough, or probably damage or whatever, and then the sense data or the reported data may be not very correct. Okay, so when you're dealing with IoT data, you have to be able to try to check the accuracy and sometimes the veracity of your data. So this is in general what we call the 4 V's. V's for volume, variety, velocity, and veracity related to big data problem. So in our case, most of us, when we're deploying IoT solutions, the meaning of the collected data can be very difficult to get. For instance, if I take a specific example of farming, what the farmer is interested in when he's having cattle, maybe cows, he's interested in fertility detection, and maybe eating, ruminating time for welfare. How does it affect his productivity? Because these 2 parameters affect the production of milk, for instance, okay? So given that point, what kind of data can be easily obtained? If you want to detect fertility, if you want to be able to determine eating, ruminating time, what type of sensors would you use? At the end, the most cost-effective one, the most simplest one, would be some kind of accelerometer data with neck-mounted collar. Okay, so if you put the collar close to the jaw, then you will be able to detect the jaw movements and be able to detect whether it's eating, whether it's ruminating, whether it's sleeping, whether it's running, whatever. Okay. Now, how to detect this even? What you get is raw accelerometer data. Okay. So the fact is, you need experts from the domain, and you need advanced data analysis tools in order to do that. Because from the raw data, you have to be able to say, okay, my data here looks like it's eating, and my data here looks like it's ruminating. Okay, so the analysis of data can be quite tough if depending on the application domain. Okay, so among all the analysis techniques, a lot of these methods rely on traditional statistical methods, and they are still valid. Okay, so don't forget this. It's not because we're talking about advanced AI or very buzzword or fancy things that the very basic statistic methods is not useful. They are still very useful, and you will see that actually most of the useful AI techniques have a lot of statistical method and lots of mathematical background in these methods. The question here is, how are we going to use these tools? Okay, even if statistical methods are still valid and useful, maybe the way we are using it right now would be different, hopefully more efficient, given the fact that we have access to much more resources than 15 years ago, for instance. So a lot of these resources right now comes from internet servers, from cloud servers, come from optimized library, come from a lot of web tools to orchestrate various tasks that you may have to do. And the idea behind using a cloud, web, or orchestration tools is to take or to squeeze out of these infrastructures the most efficient way to do your data analysis. Now, getting into the core of the talk, some years ago there has been the rise of artificial intelligence. And there's a lot of things behind artificial intelligence, but I would say that we have to make the distinction between what we call the general AI and what we call the narrow AI. Okay, so general AI is currently still quite unrealistic to have. Okay, so there has been a lot of overhyping. Overhyping means probably over expectation, okay, for general AI. And when we look at how AI methods or AI ecosystem has evolved from the early general AI expectations, where people believe they could build intelligent robots and intelligent systems that act like humans, to what we want to do right now with so-called machine learning techniques and so-called deep learning techniques, then there has been a little bit less expectation, but more results. Okay, so just to put the pictures of what we are going to look at, we are more focusing on what we call narrow AI than general AI. So general AI is, like robots, as I said. And in our case, it's more specific purpose AI, so narrow AI, where actually the techniques that you're going to apply are maybe not as generic as the general purpose AI, but maybe adapted to the problem that you are trying to solve. Okay, so it could be chess poker playing, could be image recognition, it could be assistance driving, and of course it could be smart agriculture, prediction of weather, and some kind of prediction on historical data. At the early age of AI, people said that the Turing test could be a nice tool to assess whether a system is intelligent or not. Okay, and right now, and still now, in a lot of movies, that promotes the idea of general AI, they use the Turing test in order to assess whether the system is intelligent or not. Actually, for us, it's not that important, because as it is written right here, I mean, we don't want to build something that acts like a human. Okay, just like a plane that flies does not want to mimic the bird. Okay, it extracts what is essential to fly, but it's not trying to mimic the how the bird are flying. Okay, so in our case, it's the same thing. We want an intelligent system, but the results is main is what we want. Okay, we don't want to mimic very precisely the behavior of the brain. Okay, so this is what actually all these years on AI has shown, that if you want to really go into the making the system working like a human brain, then you will probably fail. But at the end, what is interesting is the results. Okay, the result that you get. So among the dimensions that you would have, you can have systems that think like human, that act like human, and there's a little bit different because thinking and acting is not exactly the same. And systems that think rationally and systems that act rationally. Okay, so among these 4 dimensions, obviously what we can do right now for IoT intelligence is more a system that act rationally. Okay, so if I take the example of a irrigation system, acting rationally would mean, okay, I have historical data, I know what is my crop type, I know my soil type. Okay, what should I do in the next 24 hours? What should I rationally do to optimize irrigation? Okay, so this is the question that let's say IoT plus AI is going to try to answer. Okay, so I narrow down a little bit the problem just to make sure that we are talking about the same thing. Okay, we're not talking about general AI, we're not talking about science fiction, we're not talking about building robots or building systems that think or act like human, but we are building systems that act rationally in order to provide useful feedback. Okay, so there's a lot of AI technologies, and as you said, we're more focused on what we call the narrow AI. And so we can start very quickly with what we call machine learning. Okay, so from all the AI technologies that you may have heard, machine learning is one of the most useful in the case of when you want to predict something. And the principle behind machine learning is you train a model. Okay, you train a model with a lot of data sets, and at the end you will end up with a trained model that can predict the next value out of historical data. Okay, so this is the principle behind machine learning. So machine learning, the machine would learn how to understand and how to predict the next values from a training process. And again, when we're looking about machine learning techniques, there's a lot of techniques that you can use. And again, going back to what I said before, behind these techniques there's a lot of statistical method. Okay, so if you look at machine learning ecosystems, then you will have what we call the supervised learning, and I will talk about this a little bit later. And then you have the unsupervised learning, I will also talk about this later, and then the reinforcement learning. Okay, so 3 categories belongs to machine learning. Okay, so regarding supervised learning, you may have a lot of classification and regression, and this is what most of our applications, most of our, let's say, IoT applications belongs to. There's few examples of IoT applications with unsupervised learning or reinforcement learning. In our case, it's more supervised learning, and you will quickly understand why that type of model, that type of techniques suits better the type of IoT application that we are dealing with. So the idea behind supervised learning is you have input data set which are labeled. Label means the input data is tagged with the correct label. What does it mean, correct? Okay, you said, okay, this is something, this is another thing. So you train your model to be able to or to get the knowledge of what is something and what is another thing. Okay, and the whole purpose of supervised learning is once you provide the input data, the tag input data, then the system will be able at the end to predict future data. Okay, so first you train the model in order to build the system, and then you have new data coming in, and then once your model is trained, you could check whether your prediction is good or not. Okay, so an example, a typical example for supervised learning is the spam mail example. You have a database of a lot of mails, but these are labeled. Okay, you know which one are spam, which one are not spam. Okay, so this is the label, the tag label. So you give, let's say, thousands or hundreds of thousands of these label tagged mail to your system, and at the end, when you think that your system is ready, okay, you will provide new mails, brand new mails, and he will be able to say, okay, this one is a spam and this one is not a spam. Okay, based on the training, using tag data. Okay, so this is what we call supervised learning. Supervised means, okay, we provide something that we know is correct, and then we train the system with that. In terms of real techniques behind the supervised learning, then we have classification techniques, and then we have regression techniques. Okay, so spam, no spam belongs more to classification, and regression is probably what we are going to use more in IoT applications, where actually what we want to be able to predict is trends or the future values. Okay, so this is more belong to the regression, and I will have a whole set of slides regarding regression. Now, you may be curious to know what is unsupervised learning. Okay, so unsupervised learning means there's no supervision because it's unsupervised. So what does it mean? It means that you provide data that are not labeled. There's no tag, so you don't know exactly what it is. Okay, and the model will try to find correlation between this data. Okay, so let's say you don't have the system will try to find similarities, patterns, and that will try to identify clusters and exceptions. Example, you provide a lot of images like this, okay, without any tags, okay, without anything. And then the system will be able to say, oh, from all these pictures, I can see that there might be two categories, ducks and not ducks. How? Maybe because these images share some kind of similarities, okay? And these images share some kind of similarities, maybe the ear, here, here, maybe the shape of the feet, and so on, okay? So the system is going to try by itself to find similarities and then to classify a little bit. And this is more what we call unsupervised learning. Well, in our case, when we're talking about IoT data, except from the very specific application domain using images, there's very few unsupervised learning examples. Okay, so as I said, most of our IoT data, especially in agriculture or predicting values for some application domain, we're more keen on using supervised learning than unsupervised learning. So this is just to show you the difference between the both approaches. Okay, so typically what we can expect from unsupervised learning is more from clustering, okay, or association. How do you How do you cluster? How do you classify? How do you associate items all together based on the similarity pattern that the system may found? There's let's say an interesting part of learning called reinforcement learning that may be used as a complement to the other two previously defined techniques. Okay, what you add is some actions on the whole system. Okay, the actions could be rewards. Okay, could be penalty. Okay, so that actually you're adding some information to your model, saying, okay, this is good, this is not good, and of course the system will try to identify which actions is good and which action should be avoided. Okay, this is called the idea of reinforcement learning is then explained here. So one example is the robot path example. So this robot has two choices, water and then fire. And in case he goes to fire, then he got a penalty. In case he got to water, then he got a reward. Okay. So at one point, the system will try to detect that, or will detect that it's better to avoid going to water, to the fire. Okay, so this is what we call reinforcement learning. So depending on the choice, we add some kind of indication saying that, okay, this is bad, this is good. So in some time you give more information to the system. Okay. Now remind that regression belongs to the supervised learning techniques, and regression is especially important to us because in a regression model it is very suitable for predicting new values. Okay, so regression techniques are used to try to predict values within a continuous range. Okay, by trying to find mathematical relationship between these values. So let me give you an example. And first, let me set up some kind of terminology that are important when we're talking about regression. We call dependent variable the main event to understand. So here, the dependent variable is, let's say, the size of my plant, the size of my crop, or the welfare of my maize crop, or whatever. Okay, this is the dependent variable. The independent variable is the events that you suspect has some impact on your dependent variable. So typically here, amount of water, amount of sun, and temperature, whatever. You suspect, okay? Of course, in our case, we know that there's some impact, but in the right terminology, you suspect that they do have some impact, okay? So dependent variable, independent variable. So when you're using regression, it could be simple regression. And these very funny examples indicate that, let's suppose that your dependent variable is the temperature. So you want to know what is the temperature, or you want to be able to predict the temperature, whether it's hot, not hot, and so on. And it's funny here because we decided to use something that is completely, let's say, probably completely, how to say, something that we wouldn't think of at the first thought, but we decided to use the number of cricket chirp. Okay, so it's cricket, this small insect, and when it's hot, usually they produce more chirps. So we want to know whether there's a relationship between the number of cricket chirp and then the temperature. Okay, so a simple regression would try to find correlation between number of cricket chirp and the temperature. And with more complex system, we could have multivariate regression model where there are multiple independent variables. So again, here the temperature is the only dependent variable. So you want to know, you want to predict the temperature, okay, whether it's hot. So it may depend on the number of cricket chirp. The more cricket chirp, then probably the temperature is higher. But then you want to add the rainfall, the automobile traffic, because more automobile traffic maybe would increase the CO2 and would probably increase the greenhouse gas effect and probably increase temperature and so on. Okay, so you got the idea. So in the case of our system for smart agriculture, when I previously mentioned that we are interested in multiple knowledge streams in order to be able to define what is the right amount of water to put into your soil, then you would say that you would see that here the temperature can be replaced by the amount of water that you want to inject, or the welfare of your plant. And then the X1, X2, X3 could be the weather, could be the soil type, could be the irrigation techniques and whatever, okay? So here are for the regression. So usually you would use a scatter plot where you're going to have the dependent variable on one axis and then the independent variable on the other axis. And if you have multivariate system, then you will have more complex, probably multi-dimensional scatter plot system. Usually, when you are using regression, and this is important to know, when you're using regression, it means that at one point, you believe there are some correlation, okay? If you don't think there are correlation, then there's no point in using regression. In most of our physical system, there are obvious correlation. If I take again this example of soil moistures, well, typically the soil moistures, when you irrigate, then the soil moistures will increase. And when you stop irrigating, then little by little, the amount of humidity in the soil would decrease, okay? So of course, there's a correlation, okay? With time or with the temperature outside or whatever, but there are correlation. So correlation could be positive, +1, okay, when depending on the variable you have an increase. Could be negative, -1, when depending on the variable actually you are going to decrease. And these cases are equal 0 it is not correlated at all, because you can't find any correlation between your data, okay? So if you find this with your scatter plot, then it probably means that you're not going to be able to use regression at all, okay? So there's a lot of regression techniques, and just want to show the linear regression, but there are much more. And again, for those who wants to get more material on that, then maybe now you may be able to focus a little bit more what you're going to look at. Now that I've explained what is supervised learning, what is regression, if you want to move further, then I hope that it will be more easy for you to find information about regression. So there's a lot of books and a lot of materials on regression. And just want to mention that I think that it's Elsevier or one editors that release a lot of open source book, I mean in free access, and a lot of these books refer to regression, to statistical method, to machine learning. So please dig on the web and you will find a lot of very good material on machine learning and regression. Now, I'm talking about something that probably it could be interesting, but not directly related to what we call IoT plus AI, because it's a little bit beyond machine learning. It's what we call deep learning. And it could be useful in some applications. And you will see that what people call deep learning use actually a model based on the neural networks. And the neural networks is a trying, it was actually introduced at the, let's say, the early stage of the AI movement, where people still wanted to mimic how the human brain is functioning. So they said, okay, the human brain is composed of neurons, lots of neurons, okay, billions of neurons, of course. And then they say, okay, the neurons has dendrite, nucleus, cell body, and so on. So what I know from the neurons is they get inputs from the dendrites, and then it will have outputs on other axon or dendrites also. So they build a digital model saying, okay, I have something here. I have inputs, I have outputs, and based on the input, then my output can be changed in somehow. Okay, so this is what they call the perceptron, or what they call the neuron, the digital neurons. Okay, and from the perceptron or digital neurons, you may build a small neural networks. And neural networks are built by stacking all these perceptron in layers. So you will have input layer, hidden layer, output layer. And the functions you put in here in order to manage or to process all the inputs then could be adapted dynamically based on what you are going to send to the model in order to train it. Okay, so again, we have the idea of training the model, training your neural networks in order to be able to recognize something. So this is what we call deep learning. Okay, so before machine learning, before the modern AI terminology, it was called, let's say, artificial intelligence, and people didn't really believe that it could be very useful because the expectations were so high and the results were so low. But now that we know better what is AI and what is not AI, then we are more free on, or more relaxed to say that, okay, deep learning is AI, one of AI techniques, and it is good to do that, okay, and it is not good to do that. So deep learning is the generalization of the simple neural networks by adding much more layer, much more perceptron layer here. So you have one input layer, a several bunch of hidden layers, and then the output layer here. And the more layer you add, the more correlation, the more dimension you can address. Okay, so as you can see here, if I have single layer, then I can detect this. If I have 2 layers, I can detect this kind of patterns. You have 4 layers, 3 layers, I can detect more granularities into the patterns. Okay, so the more layers you have, the more power of discrimination you have. So where these deep learning techniques are essentially used in modern systems, they are mostly used in voice, face, pattern recognition. Okay, so when you're taking pictures, you upload pictures on Google Photos, and Google Photos manage to say, okay, these pictures relate to this person, and you may know this one, and so on and so on. So this is what we call deep learning. In our case, I mean, there are very few applications regarding IoT, the real IoT, you know, telemetries, agriculture, industrial IoT, and so on. There are very few applications using deep learning unless you are using images. Okay, so recall, if you have to keep something in mind, is usually image processing is related to deep learning, and data processing prediction is more related to machine learning. Well, I believe that's all, and I hope that this introduction has been useful to you. And maybe, Wilma, we can take some pictures, some pictures, some questions before we move on to the presentation from Javier on the real integration of these techniques into the Waziup solution.
Thank you, Congduc.
Okay.
Thank you. So, is there any question? Abdul, do you want to say something?
No, just wanted to. So that means that it was interesting. So, what you said that that means that the most of the IoT application, the regression learning is the mostly will be applied like kind of IoT application that we are talking about. where limited amount of data. Also, yeah, and regression, and then the unsupervised learning. I think regression is also supervised learning. It's not unsupervised learning.
Yes, regression is not
sometimes
supervised learning. Yes.
Sometimes in IoT, often we collect the data. We don't know the purpose, or maybe we know purpose, but we don't really do proper labeling of the data. And because we didn't have a proper labeling of this data, then it become unsupervised learning, right? So, but unsupervised learning, then we cannot do the regression. We can just do classification and things like that, as you said.
Yes, but on simple data, unsupervised learning is very most of the time useless, because if you don't know whether it's humidity or if you don't know whether it's temperature, then there's no way for you to know it. So unsupervised learning is more to find patterns. So it's easier to think of it using images, photos, to classify images or photos, but for simple data, for scalar data, I believe it is not very useful.
Okay, understood. So that means that there have to be somehow labeling have to be for all the data, IoT data that we collect.
Yes, labeling or data sets, how the data is evolving. Suppose that you have a pilot farm, and then you put sensors and you observe. You just observe. You're not taking any actions, but you observe what the farmers is doing. Like when he's irrigate the water, and when he's doing that for that particular type of soil and particular type of crop. So you observe that for, let's say, 6 months or 1 year, and then you got a data set, and you believe that your farmer is a good person, he's an expert, and he knows what he did. Okay, so you can use this data set to train your model, and then when you put that to another farm, then your system will be able to define using regression techniques whether what the new farmer is doing is good or not, based on what he learned from the expert. Okay, am I answering your question?
Yeah, you answered a question, but obviously I was also asking myself in the context of IoT, like you say irrigation solution, one example, let's say, and often as a IoT application developer, maybe he has in mind to develop this let's say the remote irrigation, like the water management solution. And in that cases, he has a sensor, deploy the sensor, and sensor often monitoring the soil moisture. And this application is not collecting any other level, because it's not the purpose. And when he deployed this system, this person doesn't have any vision of AI. He was just, his objective was to monitor the soil moisture sensor and to just make a decision when to put the water. So and then he didn't collect any properly doing the labeling, like the when to put the water and how much was changing in the parameter. And so that means that what you said, that those cases, this kind of data is very difficult to use, because it doesn't have really proper labeling.
Well, not exactly, because you don't need to label it. It could be labeled somehow automatically, because you may have several sensors. So you have one monitoring the soil humidity, but of course you have the time. You have the time of the day, and then you have the, let's say, the temperature, the soil temperature, and then the ambient air temperature. So you can have a mix of this data. So you just observe how the farmer, let's say, decide to irrigate depending on the temperature, depending on the soil humidity level, and so on. So you have, if you have trust in the farmer expertise, then you can say that this data set is somehow representative of what you should do for this type of soil and this type of plant. And when you transpose this to another farm, then you can use this model as some kind of reference, And what we want to do is, if we want to predict something based on other type of soil, other type of crop, then we would integrate multiple knowledge stream in order to adapt the model. So this is the way we can do it.
So, good afternoon, everybody. My name is Javier Mantila, and I work with Congduc on the development of the LoRa Gateway Artificial Intelligence Framework. So today I'm going to talk to you about how this architecture is developed and how we integrate it into the LoRa Gateway. As you can see from this diagram, it's a stacked architecture. So each layer depends or relies on the layer that is below. So I'm going to explain on detail each layer. So, well, what is it in overall, in general? Well, this interface, this architecture is an interface that allows users to build and use artificial intelligence models on the LoRa Gateway. So that means is like we are enabling the execution of artificial intelligence models. That's how they call the algorithms that are developed in this architecture. So this allows to have like an interface without going to very details of the system, and we just focus on the artificial intelligence development. It's mainly based on a Jupyter Lab Docker container, and we will talk a little bit about that in detail later. So starting with the first layer of this architecture, we have the hardware. And as the hardware for the LoRa Gateway is a Raspberry Pi, it will also be the hardware for the our LoRa Gateway Artificial Intelligence Framework. As also we know, like most modern Raspberry Pis are 64-bit based on an ARM CPU. So this has quite an advantage, and this is key to the implementation of the artificial intelligence algorithms, because this allows for much faster execution and memory management. The next layer is the operating system that allows to use the hardware of the Raspberry Pi. From the Raspberry Pi Foundation, they have their official artificial intelligence, operating system, that is Raspberry Pi OS, that is mainly 32-bit. They do it like that because they wanted to keep a backwards compatibility, but they also released a 64 versions in the recent releases. The reason of that is because there are a lot of software that is dependent on 64-bit and take advantages for those new features that come with 64 bits. Besides the Raspberry Pi OS, that is the official operating system for the Raspberry Pi, we also have other operating other operating systems that are, for example, Ubuntu Server, Manjaro, Arbian. But these operating system, they don't handle very well all the hardware interfaces that comes with the Raspberry Pi that is very specialized on sensors or actuators. Okay, moving on, then we have the containerization platform, or in this case is called Docker. So what this does is like bundles an application and all dependencies into a single object called container. And the advantage of that is like as most software, they rely on other software, on libraries. So the idea of having this is like you can isolate your application or your main software with its main or unique dependency from the rest of the operating system. So you don't have problems with version mismatching or missing libraries, you have everything that your software needs in the container. The container runs obviously using calls for the kernel in the operating system, but it is isolated from the general operating system. It's like having its own operating system for itself with the necessary and unique dependencies. So in this case, we are using Docker because it's the most famous containerization platform. Docker requires 64-bit operating system. As I said, like the hardware now allows now the execution of this kind of software. And also there are like some 32-bit releases for older Raspberry Pis, but this is very outdated and deprecated because the community is not using them really. So everybody is like out there in the scientific community and the artificial intelligence community, we are using the 64-bit versions. And now in the next layer, we have like the artificial intelligence container. This layer focus like on the specialization of one of the containers that we can create with Docker, because Docker is very general. You can have, for example, a web server container. You can have like a database container, but we have created our own container that have all the software required for running artificial intelligence models. Sorry. So the next layer will be the runtime engine. So most of the modern software and most of the software using artificial intelligence uses a runtime environment. Like runtime environment could be like, for example, the Java virtual machine or the common language runtime, and also Python. So not going into very detail, but most of the software, when you're developing software, you can do it like in two fashions mainly. Like one is compiled. So you have a source code file that is human readable. Then you use a software called compiler and translate it into machine language. That is basically a format that the computer can understand. Or the other fashion to execute, to develop programs is using an interpreter that takes the source file that again is a human readable and goes line by line, translating and executing each line of the source code. So again, lately there has been a preference for runtime environments, like again Java or .NET, or in this case Python. We have used Python in this artificial intelligence container because it's the de facto artificial intelligence language. Okay, the next layer on top of that are the packages. So as most of runtimes, they have like modules that run a specific task, mostly called, it will be like the similar of libraries. So these packages integrate specific mathematical data and techniques, and all those are again contained or grouped into these packages, and each package is very, very specific. So for example, one package could be specific for regression, another package could be specialized in classification, another package could be specialized on data manipulation, and another package could be specific for neural networks. So we are talking about these models or package for Python that allows to run those desired tasks. Next, there is a special package that is the package manager. Since there is a lot of packages, it's a good idea to have a package manager that makes the correct integration between the runtime and the library. So is and this makes life easier for the developer of the artificial intelligence models. So there are another, in the same layer, there is another specific package that is called the IDE, or the Interactive Development Environment. And this is like a software, for building programs and common developer tools into a graphical user interface. So what this means is, like, it's just a tool for developing programs. Like, you could have like a word processor, like it's Word, or you need, for example, mathematical or numerical calculation. You will use Excel to develop your calculations. In this case, this is a graphical tool that allows you to write code of the machine learning. Specifically, in this case, will be for machine learning, but you can use this IDE for other purposes. So this IDE specifically, it's one called Jupyter Lab. Well, Jupyter Lab is it's an IDE is specifically oriented for Jupyter notebooks. We will talk in detail, and I will do a walkthrough about Jupyter notebooks next. And finally, well, the last layer is the next layer is the Jupyter notebooks. This is like the front end. It's like the code that you develop inside the IDE. That is the Jupyter notebook, and Jupyter notebook allows you to write or create multimedia documents containing working code, figures, and text. So this is a small screenshot, but I will go into more detail when I give a walkthrough of the framework. So I'm going to switch my screen to a live demo. So here is the homepage of the default LoRa gateway. So we click on the web admin interface. Then we input the credentials for the admin. And what it does is we have the default. I hope you are familiar with the LoRa gateway at this time. So we are on the landing page of the admin model of the LoRa gateway, where we can manipulate and control our LoRa gateway. So right now we see on the left a side panel, like there is a new entry, a new row that is called Jupyter, and that refers for the Jupyter Lab IDE. Okay, so it takes a moment to load, basically because we are on a testing phase. But when we release the final image, then we will have faster response times. So as you can see, it looks like most of the modern editors, where you can, on the left side, you have like an aside that allows you to navigate through the file system. On the right side, you have a default launcher that allows you to execute or create documents faster. And there is a menu bar on the top. Okay, so I'm going to go to the model, to the code that I want, to the Jupyter notebook that contains the code that I want to execute. So we can see the notebook itself and how it develops. But at the moment, is there any questions?
Yes, I have a question. Hello?
Hello, yes?
Yes. Yes. Thank you for the presentation so far. It's pretty awesome. So I have a question about notebooks, and also I gather that you work in some kind of like a team setting. How, so coming from the background, the notebooks have a lot of metadata. By the just an introduction, this is Martin. I'm the hub lead in Uganda. That is the Hive Collab in relation to Waziup. So yeah, so I'm asking about the part of the notebooks and the metadata, and also how you deal with that when collaborating with the rest of your teams in terms of version control and all that. In a production system, how do you go about that in using notebooks from a production kind of level system? Thank you.
Yes. So for specifically for the LoRa gateway, there is no team software management. We are not using like a version control, because this is like an embedded device. So we don't have like, well, we have a development. I mean, Congduc and we have a development type, but when the LoRa gateways are shipped with the new artificial intelligence framework, there won't be any source control management for that. It's not like if there is Git on it or other. No, there is. We are not releasing it with that. You can install it because in the end it's Raspbian running on the LoRa gateway. If you want to, yes. Now as Jupyter, I know there is a Jupyter Jupyter Lab version for collaborative work that is called Jupyter Hub. I think you can do some queries and investigation, and that allows for teamwork, and so many people can work on the main notebook or code that you are working, and also facilitates the integration with software control management and continuous integration. But again, since the project is just like an almost isolated embedded system, it doesn't communicate with other Raspberry Pis, or it's not. We are talking like a full production environment in the sense of big application solutions. No, so that's why we see no need for use that. But again, just to answer your question, I hope you can install it. I mean, like you can install Git, you can install Jenkins or Bamboo, all the continuous integrations and source version control management that you want, and also for Jupyter, there is Jupyter Hub. But again, we don't install Jupyter Hub or any collaborative software on the LoRa gateway.
Maybe I can add something, Javier, for
Sure.
you, Martin. I mean, you have to know that the framework on the gateway is for one application, because if you deploy one gateway for a particular customer with AI features, then this AI features is trained or has been trained or has been pre-trained for this particular applications, because what you want to deploy is an operational gateway. So all the development, all the training could be done prior to that on, let's say, Linux computer or much more powerful computers, and then maybe on your development system, you may install a control version or sharing, code sharing with several developers, because you are in the purpose of developing something. Okay, but once you deploy this on your gateway because you want to test or you want to make it operational, then, as Javier said, it turns on an autonomous embedded system. So you're not going to have control version or whatever on the Raspberry, but maybe once you're developing on other computers. So Javier, I think that you can move on.
Okay, thanks, Congduc. So here we are. We have a notebook open. So one characteristic of this is like the notebook is divided by cells, and there are 3 types of cells. Well, what is a cell? It's a section where you can type code that is going to be executed. Also, another type of section or cell could be just for documentation purposes, that it will be called, well, here it's called Markdown because it's the default markup language, or just the language that it uses for do annotations, and it has like a special syntax that allows you to do syntaxes, to do formatting. And raw is just to comment. I use it mostly, it just says plain text. It's not code to execute, or it's not markup language to do like HTML, that it is a language to do presentation that is more oriented for presentational purposes, as opposite of code. That code is meant to be executed, and raw is like comment. Like if I want to just disable this cell and not be executed, I will just leave it as raw. So for example, in this case right now, we're using code. So you can see this notebook has been already executed. So that's why it has some output, but we can run it again. And as we run it again, I will go on top of this specific notebook. I'm just going to clear out all the outputs, set myself on the first cell, and run it. Select the cell and all below. So there is another thing about the cell, that it has like an index, and when it has an asterisk, it means that well, it didn't reset from. Is the order that it was executed. So this was executed at, it should have been started at 1, but because it was already executed and I didn't clear the whole order, so it starts with the last order. So what I wanted to say, there were 11 cells here, but I executed the notebook again, so the index here will be 12, and the next one will be 13, and so on. So again, this is a sample of a code cell. It may or may not have an output in this case, because if this code doesn't yield any output, then the cell doesn't show any output. But in the case of other cells, it will. Some words about this specific notebook. This notebook was the second runner-up on the Cindy challenge. That it was a challenge sponsored by Waziup in order to create and develop artificial intelligence models for soil humidity predictions. The reason that we choose this runner-up is because it was written on Python, and Python is the most, well, de facto code language used on the artificial. The number 1 was written on R. R is gaining traction in the scientific community, but it's not as spread as Python. So as we can see now, cell number 13 has been executed. So that's the next, and this cell has output. In this case, its output is a graph. Yes. So where were I? So what this notebook does specifically, as Congduc said a moment ago, it uses regression. And here we can see the regression package for it, and some other packages that are scientific packages that allow for pre-processing plotting some data. Here we have a CSV file that is called the train CSV file that it was given by the competition. That is a CSV file that contains the data of 4 fields or irrigation fields. That is fields of maize. And it has the first column is like this is your data set that it will be the input for the artificial intelligence model that in this case is a regression model. So the first column is timestamp of the collection of the sample. Then the soil humidity of the first maize field. And there is the next column is like it was the field irrigated or no. So a 0 means that it was not irrigated at that timestamp or was not irrigated at that timestamp. Here we can see a sample that it was. The same thing goes for field number 2 with its irrigation flag. Another for soil for maize field number 3. What else? And that's it. Also has other data that other columns. Sorry. So this here that is like air temperature of that it was taken for all the 4 fields, and the air humidity in this case, and the air pressure. Also there is the wind speed at that moment and the wind gust. Okay. What else? We have that on part of the data set. So, sorry, and the wind direction. So, as you can see in this data set, we are having some, because as Congduc already said, most of the artificial intelligence models, they have to be trained first, you know, in order to get a right prediction. So that's why, and also to be trained means that it makes a prediction and it's compared to the actual results, and we can see how they do differ. If the difference is very big, then it's a failed train. So the training has to be repeated until we see a very approximate prediction of the model compared to the actual reading. So for example, that trained data could be the first columns that they say they have the soil humidity for each field. And then the later fields could be more like the inputs, the independent variables, like the air temperature, air humidity percentage, pressure, and so on. So we have these independent variables, and from these independent variables, we want to know the soil humidity of the 4 irrigation fields. Another characteristic of this train data set is like it has some missing fields. Here I'm scrolling down, but that's important because sometimes there could be failure or on the hardware of the device. I mean, like the sensor they could not provide the data, or maybe that moment the gateway was not available, or so it also has to overcome this obstacle. But that was a criteria imposed by the Cindy Challenge competition. Okay, so again, we're going back onto our notebook. And then we have a small plot that is plotting the number of the sample and the percentage for the soil humidity for field number 2, or the soil humidity for field number 2, and its irrigation field, irrigation flag. So we can see that it's very spread. Sometimes it looks like a trend, but then we have like very disparate measures. So that's something that the model should be able to predict according to the other input variables. Again, sorry, we are not going to, I'm not going to explain each very small detail or going line by line of the notebook. I'm just going to do an overview and show you the results. So here is just doing some pre-processing. In artificial intelligence, you do a lot of pre-processing of the data. Sometimes the data have to be normalized, so the data set should be restrained into a certain data range. Or maybe if you are lucky enough, then the data is normalized and data from all variables, because you see that one data is percentage, for example, air humidity is percentage, but temperature is in Celsius. So you have to normalize those values in order to input to the model. Okay, so this is what these first cells are doing. For example, here we are preparing the air pressure, the air temperature. These are functions that we define that will help us to deal with the discontinuity of the data sets. As I said, that this data set sometimes it has no data. So these are functions to deal with that. Then this is like a preparation of the train of the data set that is going to be as training. So we will have our model doing a predictions and be compared to these values, and we will see how accurate is the model that we are developing. Here is doing more preparation, but in this time including the irrigation field, the flag of the irrigation field. And here in this cell we are doing the training. In this code we are doing the training of the model. So we are going to obviously this means a lot of iterations and refinement, but because we are using the library XGBoost, that is very common and used in the scientific community, that abstract us from the iterations, and we just call or use its training functions. So we don't have to program each iteration or epochs and the training of the model. So we just, in the end, we just call this a function of the package, that in this case is XGB regressor, and we assign it to a variable on our code, and we have it. I mean, this simplifies things a lot, but there is nothing that will stop you to develop your own regression software. If you don't want to use XGBoost, it's okay, fine. You can go ahead and you develop your very own. But it's a little bit of reinventing the wheel. And again, this is a package that is very active and well maintained by a lot of people around the world. So it saves you a lot of time, honestly. So you just pass the parameters of how many estimation, the learning rate. I mean, how different, how acceptable could be the difference between the predicted value and the original sample, and the state. Like, well, it has a random state that's a little bit going into the deep and the depth of the regression models and a lot of neural network models, but we can see that on another. It will be too long to explain in this session. And then we, once we have our model trained, then we do this fit, and we make it to test to predict and to compare to the value that we already have from the original dataset. Again, we have here more index manipulation functions, and now this is like the predictions. So once we have like the models, we have to use to prepare the input, from the dataset and pass it into the model. So what this cell is doing is that, like, preparing that to pass it into the model, And then the model will do a prediction. Here we can see we have defined an object called model, a model that has a method called predict, and that prediction will be stored on this variable, and that's what. So basically, yes, this again, there is nothing to stop you to do your own very own model from scratch. It just takes too much time, like really. So you just use the wheels that are already invented. And finally, this cell. It could be seen as the main function or the entry point of our own of this notebook. What it's doing here is like first it trains the model, and after it's trained, then we said, okay, we want the predictions of that model, and we are passing the data. In this case, we are passing the normalized data. So that means preprocessed. So we are passing the data, the input from the first maze field, and then we do the same thing for the second maze field, and the third and the fourth. So in order we have like these output that are the predictions for each field. But this is, I mean, this is another format of the output of the code. Could be just like message, could be graphs like we have here at the beginning. Also could be text, plain text, or in this case could be tables or tabular data. And in the end, we save our predictions on a CSV file that we have here, sample submission. So it's empty because it is still running. But it has finished, I guess. Let's see it. Let's open it again. Oh. But here on we have like on the first column the ID of the. Here on we have the ID that would mean that like the future timestamp of the prediction, and here should be the value, but I think it's still running. So that's why we don't have the prediction yet. But again, this was not, I mean, this is like a use case. I mean, we're just showing how this technology can be used. So there is no need to execute the model. For example, from this IDE, it can be run on background, from command line system or background operating systems. It could be scheduled for that. And also, so we don't overload the system for executing. The reason to have that IDE is to have access to the model and modify it on the field if necessary. I think that will be it. So is there any questions? If there are any questions?
Thank you, Javier. Before there are any questions, I would like to add something. I would like to make it clear that the system that we present is what we offer as a generic framework for the AI developer, okay, not for the AI user. So let's assume that you are an entrepreneur and you want to build, or you want to propose, or you want to develop an AI features for your gateway for these particular applications, this particular customer, okay? So this is what you are going to use, and the generic framework package everything all together so that you save time and you understand and you have a nice environment to develop and to test your AI engine, okay? But as Javier said, once you develop all this, once you tested all this, then you can make it run on as a background. So when you ship a gateway, a train gateway, then the user will get the gateway, will plug the gateway, will power the gateway, will deploy the gateway, and then everything will run on the background, okay? So your user is not going to see all this, of course. But the developer will use this environment to easily develop AI features. So this is what I wanted to add, just to make it clear.
Yes, Congduc, thank you. Just a small note. The notebook has finished, so now we can see that the values column is filled in. So here is making like on the first column is like the timestamp and the field, and the next is the value that it predicted. So in the future, so that it will be based on the previous data we have. So. Another thing that I must say, like the idea of this notebook or this model is not to be executed on real time. Also because the data input doesn't vary much on real time. Like you sample the temperature of a field 1 second. The next second, chances are that it's going to be the same, and so on. So it's going to vary, I don't know, let's say every 5 hours, there is a significant and meaningful change of temperature. The same goes for wind speed or wind direction or air pressure and so on. So there are other cases, but that is required, like real-time processing. As soon as the data varies very often in a small amount of time, so the model has to be run immediately, almost on real time. This model, because of the nature of, and we are talking specifically for the LoRa gateway that is thought and designed for rural areas, and to help people that are involved with agriculture. We know that these input variables don't change in small periods of time. They change in larger periods of time. So what I'm trying to say here is, like, it takes some time to execute this model, but this model just needs to be executed. This specific model in this case needs to be executed like once a day, let's say at the end of the day, midnight, or very early in the morning, 3 a.m. in the morning, and you will have like the prediction for the next 5 days of the soil humidity. So also this model retrofits or has its own feedback, like, okay, new data, it predicted the soil humidity for the next day, okay, and then we got those measures. The next day arrives and we have the measures and the real measures from the sensors of the next day. Then the model compares what it predicted for tomorrow, what it actually gets for tomorrow, and then compares, and then it reevaluates and corrects itself, making it a more accurate model. So in that sense, again, we're not dealing with real-time, fast-changing data. This is a very slow-paced data input. So that's why we are not very concerned with the speed of the model. Like if it takes, like, let's say 10 minutes to do the prediction, it's okay. Of course, on other cases, that will be unacceptable. But this is not the case. So any more questions?
Well, if there's no questions so far, I just want to add one remark also. As Javier said, the predictions in this case comes into a table, but again, this is a generic framework for developers. So the prediction data could be injected back to the local MongoDB databases, and using different colors, then you can use the visualization facilities of the gateway to visualize the data, and then you can visualize graphically the predictions against the historical data. So it's just a matter of how you want to integrate your final application. Okay, so just remember the framework here is for developers, and you are free to add whatever you want for the final product on top of the generic framework.
Thank you. So they talked about these jobs, the scheduling of the jobs. You know, you can this generic framework can be used to kind of because this is targeting an AI developer. So if they want to schedule, how do you go about the scheduling aspects of it from here when you're deploying? How do you specify the intervals or times?
Yes, for that, in that specific scenario, we use the facilities on services of the operating system. So, for example, on Linux machine, that would be like cron jobs. If you're familiar with that scheduling system, or for example, on Windows would be like the task manager. The task scheduler, sorry. But in this case, since the Raspberry Pi is based on Raspbian, that is a Linux variant or Linux distribution, then it will be cron jobs. So there is a way to execute notebooks headless, so without the graphical user interface. So it's like issuing a command on Linux. But we set it up on the cron job, on the task scheduler of Linux, and that's it, basically. But it's not relying on the Jupyter Lab, like on the IDE. The IDE doesn't have like that feature. We have to appeal, or we have to go to the operating system to do that job scheduling of the models.
Okay, great.
But again, it's just a matter of integration, because calling a cron could be masked by a user interface. Okay, saying, okay, which job you want to launch, and what is the periodicity that you want to launch. So this can be packaged in a GUI for the user. Again, keep in mind that this is for developers, and we package everything so that the developers can add and save time regarding the AI features. But if he wants to integrate advanced features, advanced configuration for the final users, then it can be done through a dedicated user interface that can be plugged into the into the gateway user interface. Okay, so it can be extended in many ways.
Okay, thank you. I have another question. Is that okay? Can I ask?
Yes, for me it's okay. Wilma, do we have that constraint?
Okay, yeah. So I wanted to know. This is running on the gateway. If you compare, if at all it was running in the cloud, like Wazi Cloud, how are there any kind of performance? I don't know whether that is also something like a consideration in relation to running gateway vis-a-vis running somewhere on the cloud or Wazi Cloud. I don't know whether the question is clear.
Well, maybe let me, if I interpret your question correctly, but yeah, regarding performance issue aspects, not issues. Yes, like the LoRa gateway is based on a Raspberry Pi. It's an embedded system. In this case, the Raspberry Pi, the LoRa gateway is focused and designed for open spaces. Like, it's not like data centers or highly connected places. So I'm saying this because there could be the cases that the connections to the internet would be very weak, or maybe there could be none at all. So yeah, in that case, performance is going to be smaller compared to the times or the throughput that you can have on the cloud. Yeah, obviously, because you have more computing power on the cloud. But if the LoRa gateway has access to internet and is a good connection, then yeah, part of this processing of the notebooks could be exported to the cloud. But since we don't know where we are going to land, or we don't know where the LoRa gateway is going to land, where it's going to be used, I think that the default behavior or the default course of action to take is just to assume that is isolated from the internet. If we have access, if it has access to internet, then we can maybe think on a solution that could use the resource power of the cloud. Again, we don't know, so we just take the worst scenario. That the worst scenario will be there is no internet connection, so it has to do all the computing by itself. And again, if you compare the performances between cloud with high computer power, high computer resources, and the LoRa gateway that is a small, well, relatively small embedded devices, of course, there is a difference. I don't know if that answered your question.
Yeah, that answers the question. And one last one, one small one. When it goes to the training data, how could you, maybe I missed that part, the process of, if at all there's a new training data or a CSV file, how easy or what's the process like to kind of utilize that data for retraining, or rather incorporate it into the system? Thank you.
Yes. In this case, I show you our notebook. This is the notebook submitted for the Cindy competition. So it was based on CSV files, right? But you could have like a process outside the notebook that updates those CSV files, this train with the prediction. So you can input the predicted values into the train. Okay, and then you can use, or you just keep using this very same file. But as Congduc mentioned a moment ago, we have modified that. For example, in this case, we have modified that original version from the Cindy competition to use a database. So in that case, you for example, you can set, let me see if you can say, okay, how much into the future, but also you can set like how many you have a sliding window. You can say, okay, I want to train the model again, but only with the data of 3 days ago. So tomorrow you will omit the last day, the older one, and replace it with a new day. So I don't know if I'm explaining myself, but it's like a rolling window. So you can say, okay, I just want to train with the data from the database from the last 3 days. I'm not interested anymore, or all the data that is in the database. So that's how you can deal and integrate new data that it's going on into the data set. So so a way to tackle that is to replace the CSV file with, for example, in this case, a MongoDB database. So you can include, and you don't have to use the operating system commands. You can use it with, Python libraries that interfaces with the database, and then you do the query more easily on the data set that you want to include, the new data that you want to include, or you don't. I don't know. I hope it answers your question.
Yeah, very well. Thank you.
Okay.
Martin, I just want to add from one of your previous questions regarding the performance issues for clouds. Remind that we are talking about Edge AI, which is probably one of the most innovative approach right now, because we want to have a fully autonomous system. If we are using cloud system, when it's there's a lot of cloud that actually proposes prediction models or whatever. So you just upload the data and maybe you have some similar features. But we're talking about how to embed the advanced AI features into the gateway itself. And then regarding the performance, maybe you notice that we need less than 10 minutes to run the model, okay? Less than 10 minutes, probably 5 minutes, something like this. And Javier said that you just need to run the model once a day, probably scheduled to run the model at 3 a.m. in the morning. So 5 minutes once a day. I mean, really, it really pushes for the edge AI solution instead of going to the cloud and putting data to the cloud and getting data back to the cloud, especially in rural areas.
Okay, a quick one, just an afterthought. Are you still there? Yes.
Yeah.
So for the part of maintenance of the gateways, I understand that kind of a person has to physically go to, and do stuff on the gateway, maybe kind of upload a new image or something like that. Is there a possibility of kind of, exploration of the possibility of handling some of kind of updates of these notebooks or something remotely? I don't know whether the question is clear.
Yeah, I think so. So again, like because we are using Docker containers, then that will help a lot. Like the models run on containers that could be updated regardless the operating system version that you have below. So, but in the case, if you have internet connections, yes, it could be updated remotely through the internet. We just deploy a new container, Docker container, and that will have the upgraded versions of the notebooks and so on. But in the case of rural areas, I think you will have to have the update could be, and correct me, Congduc, if I'm wrong, like to do those kind of updates where there are no internet access. You may have to do physical update with a SD card that it has a new image release, a new release of the image of the LoRa gateway.
Yes, unfortunately, if you don't have internet access, then it's the only way to do. Package everything from what Waziup will provide, and then change the SD card. But also remind that you probably need a new environment for the 60-bit OS. So if we think of all the gateways that has been deployed so far, in order to get full usage of AI features, you need the let's say at least the 64-bit OS in order to be able to run the full 60-bit tools of AI. So I believe that since the AI features are right now not well developed, we are preparing the whole framework for the future. Then we will release very soon 64-bit images with all these things packaged, and once the gateways has been updated physically with these new images, then we will be able to update only the container periodically. Yeah. I don't know if I answer your question.
Yeah, definitely it does. Thanks.
Okay, great.
Hey, I think I have a question. Thank you, Congduc, and thank you, Javier, for this great presentation.
Yeah,
what I want to know is there a requirement for the Raspberry we can use for that? Can we use previous version of Raspberry Pi, or we need to start with the version 4?
So the main requirement will be like it has to be a Raspberry with a 64-bit ARM processor. So as my knowledge that will be Raspberry Pi 3 and above.
Yeah,
Yes.
3 and above. Okay.
Yes.
Okay, I'm getting. Yeah. Okay.
Yes, I confirm. We run the whole packages in native 64-bit version on Raspberry 3 and above. Okay, so you don't need to upgrade to Raspberry 4. It's not mandatory. If you do have a Raspberry 3, it's fine because it has a native 64-bit ARM microprocessor.
Okay, thank you.
You're welcome.
A quick one. Is there a quick one? Is there documentation of this procedure of these things like online or somewhere? The nitty-gritty details of this process.
Well, we are preparing the document, so we hope that that we can have a draft document by end of June, for instance.
Hello, I want to add something here. So for this AI thing, I've been also working on a data, let's say, sensor simulator. So it's like you have your own sensors on Waziup, and then you search on it, and then you add real data and the interval that you want, it pushes to Waziup. It's almost done, just some tests is remaining, so I'll finish it soon. So it's basically going to be a service on the Waziup. It crawl thingispeak public API, collects all the data from there, and like periodically it just keeps collecting in the background. So it has a huge kind of database of sensors. You can search on it and you can configure it how to push data to your sensors that you are defined on Waziup. So far we have like 4 million over 4 million sensor values collected, because I just run the code. Sometimes I just stop it. So in middle of that when I'm running, it just keeps running and collect data. So just shortly we will announce that and like everybody can use it.
Okay, great. Thank you, Moji.
Thanks.
Yes, I mean, in the various project, we are deploying a lot of piloting sites with real sensors on fields. So this data can be used as data sets.
Yes, because they are also real sensor data, like from anywhere around the globe. You can basically use it.
Okay, should we stop here?
A quick one, Congduc. Yes, I wanted to ask, in your intro, you talked about how some of these models require, or majority require, some element of utilization of data from elsewhere, from other sources.
Yes.
So I was wondering, in case, let me say, for this model, maybe you also want to use weather data, you want to use even other data, maybe, I don't know, any data that is not being captured by the device itself. I don't know whether I missed that part, but I don't know how that is accommodated when it comes to this setup. Thank you.
Well, at least your model has to take into account the new parameters somehow, and then you can get data. I mean, updated data from open channels, for instance. So if you want to get weather data, you may want to seek for open data from weather channels related to your region. But then, of course, your model has to be able to take into account this data, this weather data, in order to predict something. But there's a lot of sources of open data, satellite data, weather data, knowledge databases that you can use on, and we are working on providing some kind of multi-knowledge stream frameworks. So how it fits what Javier has been presenting, it means that we can we can build a template, a Python template or Jupyter Lab template, showing how we can use multiple knowledge streams. And then the developers, the final developers, could use this template to build its own specific model.
Okay, makes sense. I'm assuming some of that external data could be through API access. So that template also kind of can be able to kind of mimic that process.
Yes, because if I don't know if you noticed, but in what Javier shown in his screen, I mean the various blocks, the various cells, there's a lot of generic code in Python. How to open the database, how to format the data, how to call the functions to train the model. So a lot of these things are actually generic to most of the models. So it could be the starting point for a template, so that developers could enrich the existing code to produce its own final code.
Cool, thank you.
Okay, should we stop here, Wilma?
Yeah, can you hear me?
Yes, I can hear you.
Okay, so I think we can stop here if there are no other questions. So, yeah.
Okay, so thank you all. Thank you, Javier, for your nice presentation, and thank you all for coming to this webinar on AI. And I hope that you learned something today, and hopefully you will get new ideas on implementing AI features.
Yeah. Thank you a lot, Congduc. Thank you, Javier. Thank you.
Thank you.
Thank you.
Thank you.
Congduc.
See you then.
Thank you.
Bye-bye.
Yeah. Bye.
Bye.